Welcome everyone to today's Explainer. I am absolutely pumped to guide you through this one because we are taking on a genuine, real-world measurement mystery. Today, we're going to unlock the secrets of trigonometry. Now look, I know that word can sound a bit intimidating. It usually brings back memories of really complex math textbooks, right? But today, we're not just staring at abstract numbers. We're going to look at the geometry of the actual physical world. We're basically going to build a mathematical tool belt that will allow you to measure the unmeasurable. Okay, let's dive into this. Imagine you're standing on the ground and you're looking way up at the very top of a towering monument, something like the Qutb Minar. Here's the big question. Can you find the exact height of that minar without actually walking right up to it with a giant tape measure? Well, the answer is a resounding yes. And the secret key to pulling that off is exactly what we're exploring today. So here is our roadmap for the Explainer. We'll start with the measurement mystery, then go through core trigonometric ratios, specific angles, key identities, lines of sight, and finally, we'll wrap up by solving real-world problems.
Let's kick things off with Section 1, the measurement mystery. You know, early astronomers in ancient Egypt and Babylon actually used these exact same concepts to figure out distances to the stars.
It's true. We are definitely not the first people to wonder how to measure distant objects. This actually brings us to a fantastic quote from the mathematician J.F. Herbart back in 1890. He said, "There is perhaps nothing which so occupies the middle position of mathematics as trigonometry." What he means here is that this subject perfectly bridges the gap. It connects the basic geometry of shapes that you probably already know directly to the highly advanced physical sciences and engineering techniques we use today to do things like build skyscrapers or even launch satellites.
So, what exactly is it? Well, if we break the word down into its Greek roots, it's actually incredibly literal. Tri means three, gon means sides, and metron means measure. That's the whole shebang. Trigonometry is simply the study of the relationships between the sides and the angles of a triangle. That's it. We are just learning how the angles inside a triangle dictate the lengths of its sides and vice versa.
Moving right along to Section 2, Core Trigonometric Ratios. It's time to introduce the tools.
I want you to look at these not as abstract letters, but as mechanical tools that are linked directly to the physical sides of a right-angled triangle. Here are our 6 core tools. Sine is the ratio of the opposite side over the hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Then you have the inverses, cosecant, secant, and cotangent. Those just flip the first 3 totally upside down. So the crucial point is this: they're all interconnected. If you know the lengths of the sides, you can find the ratios. And if you know just one of these ratios, thanks to the Pythagorean theorem, you can actually figure out all the rest. It's like a giant puzzle where one piece unlocks everything else.
All right, Section 3, Ratios of Specific Angles. This is where we look at 0, 30, 45, 60, and 90 degrees.
In geometry, and honestly in the architecture all around us, certain acute angles show up over and over again. Now, what's really interesting about this slide is the beautiful, predictable pattern hidden right there in the numbers. Look at the row for sine, moving from 0 to 90 degrees. The values go from 0, steadily increasing up to 1. Now look at cosine, right below it. It does the exact opposite. It starts at 1 and decreases down to 0. They perfectly mirror each other. Recognizing patterns like this is absolutely crucial. It's exactly what helps you master the geometry around you.
And stemming right from that table, we arrive at this incredibly important, wonderfully simple fact, the number 1. The value of sine or cosine for an acute angle never ever exceeds 1. Why is that? Well, because the hypotenuse is always the longest side of a right triangle. Since sine and cosine are calculated by dividing a side by that longest side, the result mathematically has to be 1 or less. There's just no way around it.
Section 4, Key Trigonometric Identities. Let's talk about your shortcuts.
If our ratios are our tools, then these identities, they're our cheat codes. They're universal rules that govern how these ratios interact. An equation involving trigonometric ratios is called an identity when it's true for all values of the angles involved. Here are the 3 big ones you absolutely need to know. Sine squared A plus cosine squared A equals 1. Secant squared A minus tangent squared A equals 1. And cosecant squared A equals 1 plus cotangent squared A. So whenever you're faced with a complex expression in a problem, you can use these identities to instantly simplify it. They're absolute lifesavers.
Moving to Section 5, Elevation and Depression. This is where our line of sight interacts with the math. Let's step back into physical reality for a second, and this brilliantly illustrates what I mean. Imagine a girl looking up at a kite in the sky. The straight line from her eye to the kite is what we call her line of sight. Because she has to physically raise her head above the flat horizontal level to see the object, the angle formed between that horizontal line and her line of sight is called the angle of elevation.
Now contrast that with this situation. Imagine a girl standing on a balcony, looking down at a flower pot on the ground. Her line of sight is now angled downwards. The angle formed between her horizontal level and this downward line of sight is called the angle of depression. Let's firmly anchor this difference because mixing these two up is a classic mistake. Angle of elevation, the line of sight is above the horizontal level. You're looking up. Angle of depression, the line of sight is below the horizontal level. You're looking down. Once you can visualize this in your head, turning a word problem into a geometric triangle becomes incredibly easy.
And finally, Section 6, Solving Real-World Problems. Let's put these tools to work.
We have our tools, we have our identities, and we know exactly how to map our sightlines. Let's see how this builds into a practical solution and return to our initial mystery, measuring the unmeasurable. If you want to find the height of that minar, here is what you do. Step 1. Identify your distance from the base of the minar and figure out the angle of elevation to the top. Step 2. Choose the ratio that connects what you know to what you want to find. If you know the adjacent distance and you want the opposite height, you use tangent. Step 3. You just plug the numbers in and solve the equation. Boom! In 3 simple steps, you have deduced the exact height of a massive structure right from the ground.
It really is like having a superpower, isn't it? You are now equipped with the mathematical mechanics to bridge the gap between simple geometry and the massive world around you. So, my final question for you is this. Now that you have the secret key to measuring the seemingly unmeasurable, what towering monument or distant object will you calculate next? Thank you so much for joining me on this explainer, and hey, happy calculating!